Hi, this video is about Chapter 6, Applications of Newton's Laws. This is actually a continuation of Chapter 5. So we will continue applying F equals ma that we learned in the previous chapter. But in this video, particularly, we will talk about frictional forces, strings and springs, and other stuff related to connected objects or circular motion. And you will also learn in this chapter that it will be impossible to walk without friction. If there was no friction, you would keep doing this and you would not go forward if there was no friction. So we will learn about these things. Okay, let's start. So the friction force, the direction of friction is always opposite to the force. It could be push or pull, or it's also opposite to the motion. So if an object is moving with velocity v in the right direction, the friction will be in the opposite direction. Or if you have an object, if you pull that object with force F, the friction will be, if you pull it to the right, friction will be to the left. If you pull it to the left, the friction will be to the left. Of course, for friction, you need a surface. The object, when the object is on a surface, we can talk about friction. Mu, this is a Greek letter mu. Mu is friction coefficient. It's some number, usually between 0 and 1, but it could be higher than 1. And it depends on the type of both surfaces in contact. So, for example, the box could be rubber and the surface could be concrete, or it could be glass and the surface could be steel. So in each cases like these, the friction coefficient mu is some different number. Leonardo da Vinci observed that the friction force does not depend on the area for a given object. So if you have one object like this, it looks like a suitcase. For that given object, you can pull it in this configuration, or it's completely down like this, or it's standing on the small surface. But in all cases, the friction force is the same. So in all three cases, the friction force is the same. So there are two kinds of friction forces. The first one is what we call static frictional force. It keeps an object from starting to move when a force is applied. Okay? And the static frictional force has a maximum. For example, there is this block here. Its velocity is 0. There's no force, so we cannot really talk about friction here. The friction force will be 0 here. But in the second case, the block is pulled to the right, so there is a force in the right direction. So there will be some friction, even though this box is not moving at the moment, because the force is not enough to move it. So the friction force is, in this case, is equal to the force applied. It's not moving, but in this case, there is a friction force on the block. So this is static friction because it's in action when the block is not moving. The same thing here, you are pulling it now stronger. There's more force, but still the object is not moving, so it's still the static friction. Now, at some point, if you keep increasing the force, the amplitude, of course, you will at some point win against the static friction, and then at that point, the block will start moving. So the friction, as the block moves, the friction applies, the frictional force on the block will be different. It's called kinetic frictional force. And it occurs when the object is in motion. So for static friction, we will have static friction coefficient, mu s, and for kinetic friction, it will be mu k. So for the same object, which is a wooden block here, and the surface, let's say it's concrete, these numbers, even though they are the same objects, same surfaces, these numbers are different. So you have to decide which one to use depending on the problem, because they are usually different numbers. Okay, so here, if the chair is moving, then what should we use? Well, moving means kinetic, right? If the chair is moving, we have to use kinetic frictional force. Someone is pushing the chair. If the chair is moving, we will use kinetic friction force. Kinetic friction force is, what is the formula for it? It's the normal force times the kinetic coefficient, kinetic friction coefficient. Here, N is the normal force. Okay, it could be that, you know, the person is maybe pushing the chair with little force, even though he is pushing, you know, the chair is heavy, so it will not move. If that's the case, if the chair is not moving, then use static friction coefficient, which is mu s. Look at the indices here, mu s, mu static, and this one is mu kinetic. Static frictional force at a given moment may take a value between 0, so it could be 0 if you don't push the chair, you know, well, there's no friction, or it could be some maximum value. So the person is pushing it lightly, and then there's some static friction, the chair is not moving. If he pushes it hard, and if the chair is not still moving, then still there is some static frictional force, but it's now a little bit more. So it can increase from 0 to up to some maximum value. What is that maximum value? How do you calculate it? Well, it's just like this formula, except we will use static friction coefficient. So as you push the chair with more and more force, the static frictional force will increase. When you're pushing force exceeds the maximum static frictional force, which is this value here. If the applied force, what is the applied force? It's this force. Well, it's actually the component, the x component in this case. So that Fx, if it exceeds the static friction force, what happens? Then the chair will start moving. So after the chair starts moving, after that point, we will not, so in the free body diagram, if you want, or in our calculations, after that point, we should use kinetic friction coefficient. So after that point, if it's moving, when moving, we will calculate the friction force as mu kinetic times normal force. But when still means not moving, we will calculate the friction force as mu static times normal force. Okay, so here's a table for typical coefficients of friction. So the first one is rubber on concrete, dry concrete. So you have, let's say, a rubber block. It could be a eraser that you use to erase things from the paper. And this could be a concrete. In this case, the kinetic coefficient, if the object is moving, you have to use 0.8. If the object is not moving, it could be some number between 1 and 4. And you can look at different coefficient here for different objects: wood on leather, copper on steel. If you go down here, steel on ice, it's getting smaller and smaller. And wax ski on snow, it's even smaller. And Teflon on Teflon, it's also smaller. If you look at the smallest one, it's the joints, the friction in joints, human joints. It's really, really small. Okay, so what makes us walk, what enables us to walk, is actually the friction force. Friction force is good. It's if there was no friction, we wouldn't be able to walk. So let's look at the forces on the foot. Let's say this is your foot. What forces are there? So when you step on the ground, what you do is your muscles here, you know, the leg muscles here, they're actually pushing your leg, pushing your your foot, or pushing the foot in the backward direction. So that's this force. It's the force on the food due to the muscles. So if there was no friction on the ground, what would happen? Well, your food would basically slide, right? It will just go in this direction if there was no friction. So you would look like this person trying to walk on a frictionless surface. But of course, on the ground, there's friction. So because, remember, if you have an object, if you pull it to the right, then the friction force will be in the opposite direction. Okay, so there is a friction force in the forward direction. So this is your walking direction. Okay, and the reason that I'm using static friction is because your feet is not like this, right? They're not sliding. Here they're sliding. In this case, if there was any friction here, I would use kinetic friction if there's any. But in this case, here it's not sliding, right? So that's why I'm using static friction force. Yes, the body is moving to the forward, but the foot here, when it steps on the ground, the foot is stationary, it's not sliding. So static friction force on foot applied by the ground. So this ground is applying static friction force on the foot. It prevents this static friction force. It prevents the foot from sliding back. If the foot is not sliding, then it's static friction. So we have to use static friction. If there was zero friction, let's say it's almost like trying to walk on an icy surface, because the friction is extremely small. I'm sure you experienced this. It's extremely hard to walk on an icy surface. And if it's completely zero, then this couple in the animation could not come together. So friction is good. It enables us to walk. Think about this situation. There's no way, if there's no friction, then you cannot really pin your foot like this on the ground. Here, what pins the foot, what makes it stationary still on the ground, is the friction force. So that when it's pinned on the ground, like it's fixed on the ground because of this friction force, you can push yourself, your body, to the forward. But if there's no friction, you will look like this person. He is walking, but he's not moving forward. Okay, let's do this exercise. If there's friction between the block and the ground, so you have to read the problem really carefully. In some problems, there's no friction. In some problems, there is. And so there's friction between the block and the ground. And if the initial velocity of the block is 4 meters per second, how much distance will the block go before coming to a stop? The mass of the block is given. The kinetic coefficient and the static coefficient of coefficients of friction are given. So you have to choose which one to use. That's up to you to choose the correct one. So what do we do? First, we start with the free body diagram, right? Let's first show the forces on the block. So there's going to be some weight, which is always mg. There is going to be a normal force, not always mg, but sometimes mg. We will now calculate what it is. Now the block is moving to the right, even though there's no force, but it has some initial velocity. So if it's moving to the right, then on the block, there will be some friction force. Now think about it. Is it going to be kinetic friction or static friction? What do you think? Well, if the block is moving, then it should be kinetic friction. So I'm going to put here K. If you want to do a separate free body diagram, it will look like this. So the normal force, weight, which is mg, and there is this kinetic friction force to the left. Okay, so once you get the free body diagram, you can draw it separately, or you can show the forces on the block I recommend doing it separately because it becomes more clear. Then after that point, we will apply F equals ma, F net equals ma for x-axis and for the y-axis. So for motion on y, so let me write just y motion. So what happens in the vertical direction? Well, this object, the vertical forces are normal force and mg. So we will write F net equals F net y component equals m acceleration in the y component. Is this object going down or up? No, it doesn't. So it's on the surface. So there's no acceleration in the y direction. Then this is 0. So F net equals 0. So what is F net? Well, let's choose a coordinate system. I'm going to choose this one, x, y. So right direction is positive, up direction is positive. So normal force, then this comes with a positive sign, and weight comes with a negative sign with respect to this coordinate system. So normal force minus mg equals, now there's m, but there's no acceleration in the y direction, so this is going to be 0. From here, what we find is normal force equals mg. This is not always the case. Normal force can be something different, but in this problem, it's equal to mg. I'm making this warning because sometimes students think that normal force is always mg, but no, it's not always the case. Okay, now let's do the same calculation, F equals ma, but for the in the horizontal direction. So now we are going to have F net x equals. By the way, what was the question? The question was how much distance will the block go before coming to a stop? Because there's friction, it has some initial velocity. It will go some distance and stop, right? Because the friction force is pulling it in the opposite direction. So we will calculate the distance, so let's call it x, that the block goes when it stops. So there will be some acceleration, well, in fact, deceleration, right? It's slowing down. What is that deceleration? We will actually calculate it, what it is first. From F net equals ma in the x direction. So, okay, so what is the net force in the x direction? Well, look at the free body diagram. The only force in the x direction is the friction force. And with respect to this coordinate system, it's in the negative direction. So it's basically negative Fk equals max. Now, if you remember the definition from the previous slides, the friction force definition is mu k times normal force. Okay, and in this problem, we found normal force to be just mg, so I'm going to plug it here. So the friction force will be mu k m times g. Okay, let me write it here. So negative mu k mg equals m times ax. So you can cancel these m's, and from here what you find is ax equals, it's basically negative, what is mu k? Mu k is 0.4. And what is g? G is, let's take 9.8. And from here, what we find is negative 3.9 meter per second squared. So the negative sign also shows you that it's deceleration, it's slowing down. Now, the last part is calculating how much distance it goes. So we're going to calculate x now. So this is the acceleration. So how do you calculate x? So what you can do is, there are different ways to do it. The easiest one in this case is using this formula. V final squared equals, here x component, V0 x component squared plus 2 A delta x. Okay, what is the final speed? It's 0. What is the initial one? It's 4, given in the problem here. So 4 squared plus 2. The acceleration we just calculated here, it's ax, negative 3.9 times delta x. And delta x is this distance here. So if you do the calculation here, you find delta x to be 2.1 meter. So this is the final answer to this question. Okay, here is a follow-up question. Now the second part of the question is, how long will it take to stop? So previously we calculated the acceleration to be 3.9 meter per second squared. So how do we calculate the time? Well, in this case, I would use this equation. The velocity at any time, it's initial velocity plus at. So we are going to calculate t here. So the final velocity is 0 because it stops here, right? So v becomes 0. So it's going to be 0. What is initial velocity? It's 4 in the positive direction. What is acceleration? It's negative 3.9 times t. So if you solve for t, so put the 4 to the other side as negative 4, and just cancel out the negatives, and it will be 4 divided by 3.9, which gives you 1.03 seconds. So that's the time that it takes for the block to stop because of the friction force. Okay, here's another example. In this example, the total mass of the boy and the sled is given to be m. For a given static friction, so the boy is not sliding, he is just staying like this in equilibrium. For a given static friction, what is the possible maximum angle, theta max? What is the maximum of this angle so that the boy doesn't slide down? You know, if the angle is like this, of course, the boy will not slide down. But if the angle is too steep like this, well, it will slide down. The friction in this case will not be enough to balance its weight. Okay, first of all, for this problem, for these kind of problems, for inclines, I would use a coordinate system where x would point parallel to that slope. So I would use this coordinate system, not this one. This one, I mean, you can use this one as well, but it will be harder to solve the problem. Why am I using this coordinate system? Because the nice thing about this is it reduces the problem into one-dimensional problem. Why? Because the boy is not moving up or down in this direction. So that direction doesn't really, concern me. So the problem becomes just one-dimensional, which is in this dimension. But if you take this coordinate system, the problem, the boy would, if he's sliding, he would go in this direction. The problem would be two-dimensional problem. Okay, the first thing is to do the free body diagram, right? So the boy there is this normal force. Why do we have a normal force? Well, because there's a surface. When you have a surface, and if that object is on the surface, there's a normal force. And you will see that it's not going to be mg, it's going to be something different. In the down direction, we have weight, which is always mg. And in this direction, there is the friction force. Now, in this problem, we will take static friction because the problem itself says, we don't want buoy to slide down, so we want it to be static. Okay, so for this coordinate system here, and the normal force is in y direction, that's good. Friction force is in the x direction, negative x, that's good. But this weight, mg, is kind of diagonal, so we have to find the components of mg. Okay, so I have to find this component, and I have to find this component of weight. To be able to find these components, I first have to find either one of these angles, either this one or this one. So here in the figure, it's given, but if it's not given in the problem, how do you find it? You can use different triangles to find it. What I would do typically is if you, for example, if you just extend these lines. So what I have here is basically I have a theta here. So this theta is usually given. Let's say we don't know this theta yet. So if this is theta, then if you think about this large triangle, maybe you can also extend this. If you think about this large triangle, or this one, even think about this one, this part is 90 degrees, so this would be not theta, but 90 minus theta. So we are looking at this triangle. So now add all the angles, 90 degrees, 90 minus theta, and theta. If you add them up, they add up to 180, which is right. So this should be 90 minus theta. And because this is 90 degrees here, if this is 90 minus theta, then this angle should be theta as well. You have to do this once on your own to figure out that this is theta here. And if this is theta, then this one would be mg times cosine theta, right? Mg cosine theta. And this one should be mg sine theta. Now, because I will use the components, now I can forget about this. So if you look at the free body diagram, now everything is in the y direction and x direction with respect to this coordinate system. So that's good. So I can start making the calculations now. Okay, let's start with the motion on y direction. So we are just doing the same thing over and over again. Draw the free body diagram, then apply F net equals ma for x coordinate and y coordinate. So here we will do F net y component MAY. So what is the net force in the y direction? Well, there is N and there is mg cosine theta. Which one is going to come with positive and which one will come with negative sign? Well, normal force will come with positive sign because it's in the positive y direction. So this is going to be normal force. And mg cosine theta will come with negative sign because it's in the negative y direction with respect to this coordinate system that we chose. So it's going to be negative mg cosine theta equals. Now, is there any motion in the y direction in this problem? No. The buoy is always on the surface, so it's not going into the surface or going up in the air. So then there's no acceleration, and there's no really, there's no really net force. That's the meaning of it. So the acceleration will be 0. Now from this F equals ma, we find the normal force to be mg cosine theta. Okay, this is what I was telling you in the previous slides. And normal force is not necessarily mg all the time. There are cases it is mg, but as you can see in this problem, the normal force is not equal to mg. Okay, so let's move to motion in y. Sorry, in x. So I'm going to do the same thing, except now for the x direction. Okay, now what are the forces on the x direction? Well, there's the friction force and there's the mg sine theta. Which one comes with the positive sign? Well, mg sine theta, because like this down direction is the x direction, positive x direction is the same as the mg sine theta. So this comes with positive sign. The friction force will come with negative sign. So, and remember, those negatives and positives are completely related to the coordinate system that you chose. If you choose a different coordinate system, then those negatives and positives will look different. So mg sine theta, I'm writing f net in x direction, mg sine theta minus the static friction force equals m a x. Now, if you look at this, the problem again, the question, so that the buoy doesn't slide down. We don't want the buoy to slide down. We want it to stay like this. So then in this case, ax is also 0. So from here, what I can write then, mg sine theta equals the static friction force. Now, what is the static friction force? It's mu s times n. And the normal force, we found it up here. I can substitute it here. So it's going to be mu s mg cosine theta. Okay, let me write it again. So mg sine theta equals mu s mg cosine theta. Now I can get rid of mg's from both sides. And if I divide both sides with cosine theta divided by cosine theta. So what I get from here is tangent theta, because sine divided by cosine is tangent. And on this side, I have static friction coefficient. Now the question was, what is the maximum possible angle for this equilibrium? So we started, we calculated everything with respect to the equilibrium. Then the maximum angle in the equilibrium will be inverse tangent, static coefficient, friction coefficient. So for a given mu s, this is the maximum angle that you can put the buoy and the sled so that they won't slide down. For a given mu s, if you have this angle larger than this value, this is some value. So maybe mu s is, let's say, 0.1. So this is some value, maybe, let's say 20 degrees. So if you increase that theta, if you have more than 20 degrees for that given mu s, then the buoy will slide down. So that's the answer of this problem. Okay, here's another question. In this question, it says, so there's this luggage, and it says, find the friction force here. So the luggage has, let's look at the free body diagram here. It has the weight, which is mg. It has there's some external force pulling it in this diagonal direction. There is, well, because it's on the surface is pushing the luggage up. So there's the normal force. Remember, normal force is the force on the luggage, not on the ground. The force on the ground, we are not really interested in it, but if you ask what it is, it's negative normal force. We talked about this in the previous video. But remember, when we draw the free body diagram, we are always interested in one object at a time. So the object of interest here is the luggage. So there's a normal force, and because it's on the ground, there is also the friction force. Okay, how do you calculate the friction force here? Well, if you, again, we're going to do F equals ma. Now, for in the y direction, what is the net force? So I'm going to write F equals ma for the y direction. But because the luggage is not going up or down, it's not accelerating in the y direction, the acceleration is 0. So F net equals 0 in the y direction. So what is the net force? Well, there is this normal force in the up direction. What are the forces? The other force in the up direction is Fy, right? Y component of this force. They are coming both with positive sign because they are in the positive up, positive y direction. So normal force plus Fy, and there's also weight. It's in the negative y direction, minus weight equals 0. This 0 is coming from here. So if you solve for normal force here, just put this Fy and the weight on the other side, the normal force becomes weight minus y component of the external force. Now, what is the friction? Well, always, friction definition is this. So always you have to find the normal force. First, you have to calculate the normal force to be able to find the friction. Now, we just calculated normal force here. That's here. So friction force definition is mu times normal force, and normal force is weight minus Fy. Weight is mg. Fy is, now look at this angle is theta. Then this component, F times sine theta. So F times sine theta. So this is the friction force for this luggage. Now, if you are interested, we can also ask this question. What is the force applied by the luggage on the ground? Now we are talking about the ground. We are done with the luggage, we move to ground. Now, the statement here follows is always true, okay? If the ground pushes the luggage with the normal force N, the ground is pushing the luggage with the normal force N. Remember, this normal force is the force on the luggage. Then the luggage will push the ground with negative N. This is always true. And this is actually Newton's third law, right? Action and reaction. And as for this statement, it's sometimes true, but not always. So sometimes normal force may be equal to mg, sometimes, but not always, but not in this case. In this case, normal force we calculated to be mg minus Fy. But the first statement here, it's always true. The ground, so the object, in this case the luggage, pushes the ground with negative normal force. Never say negative mg. It could be negative mg depending on the problem, but for example in this problem, negative normal force is not negative mg. Negative normal force, which is the force that the luggage pushes the ground, is actually negative mg plus Fy. Okay, now here we have another interesting question. The question is, what should be the acceleration of the cart so that the box of mass won't fall? The friction coefficient is given as, it's not a numerical problem, we are going to use the variables. So the friction coefficient is mu s. Now you are, let's say you are in the supermarket and you are just pushing the box, the cereal box here. You're not, it's not tied here, it's not glued, you're just, holding here, and then you push the cart really fast with huge acceleration. The question is it possible that this box stays here, not falling down? There was one movie, probably you remember, maybe it's I think it was Kill Bill. In one scene, the lady was running really fast on the beach, trying to keep the hat on her chest without holding it, but just, you know, but just using the acceleration, you know, running. Is it possible? We will try to find the answer to that question. So, as always, what is the first thing that we do? We find the object that we are interested in this case, it's the box, and we show the forces on the box. Now, the box, so there's this object, the cart, so it will definitely push the box. So there will be a normal force. See, the normal force is not vertical here, it's horizontal. It can be. The normal force is not necessarily coming from the ground. It could be coming from any object, and it could be in any direction. And but normal force itself is not keeping the box there, right? There should be some friction so that the box stays there. Let me first do the mg. So which direction the friction should be in? Well, mg, the gravity is pulling it down, so the friction will be in the opposite direction to the motion or the forces. So there will be some static friction. Why static? Because we want this box to be still here, not move in y direction, not slide down. You can also do the free body diagram separately, but I think that's already clear. So what we're going to do is we're going to write the motion, the F equals ma for motion in x direction. So F net x component equals max. So the only force, let's use this coordinate system, x and y. The only force in the x direction is just normal force, right? So it's going to be normal force equals m times acceleration x. So without acceleration, you have zero normal force, and if you don't have normal force, then there's not going to be any friction, because the friction force, it depends on the normal force. If you have more normal force, you have more friction, right? Why? Because if you have a block on the ground, let's say if you have a block, if you push the block, there will be more friction, right? Because the normal force becomes larger than mg. Even for mg, if the normal force is equal to mg for the block, you still have friction force. But if you push it further, in addition to mg, if there's force, then there will be more friction because there will be more normal force. And I'm sure you experience this in real life. Okay, let's continue with our problem here. So what's asked is, what should be the acceleration of the cart? So it's actually asking ax, right? So ax will be, from this equation, it will be normal force divided by m. Okay, we haven't found normal force yet, so we have to find the normal force because the answer should be in terms of mu s, maybe mg, and other variables in the problem. So for that, I have to do the calculation for y motion. So motion in y direction. So in this case, F net in y direction will be m times ay. Now, I want this to be specifically 0. Why? If there is acceleration of the box in the y direction, that means the box is falling down. I don't want it. So I want it to be 0. Now, let's think about the forces. Up direction, I chose it to be positive, so the friction force for this coordinate system, it will come with positive sign. So we are going to write F friction, and I will subtract mg because mg is down. Down is negative in this coordinate system, right? And this would be equal to 0 because you want acceleration to be 0. Now, the definition of friction force is mu s times normal force. Now I will take mg to the other side. Okay, and let's write the normal force here. The normal force is m times, or let's find normal force from here. So let's calculate for the normal force. Normal force is equal to mg divided by mu s. Now what I'm going to do is I'm going to calculate ax. That's what the problem is asking, right? So ax should be, well, here, if you look at what we did here, it's normal force divided by m, and we already found the normal force. Let's plug it here. So this is going to be mg divided by mu s divided by m. So there's 1 over m here. So these m's cancel. And we found the acceleration to be g divided by mu s. So for this problem, for the cereal box to stay here, how much acceleration do you need? You need g divided by mu s. And interestingly, it doesn't depend on the mass of the object. So it depends on the gravity, which is 9.8 for the Earth, and it depends on the kinetic static friction coefficient between the box and the cart. Let's think about, let's think if it's possible, if it's really possible to do this. Let's think about some of the values of g and mu s. So this was the calculation. If you can get this much acceleration, then it will be possible to keep the box here. Otherwise, if it's less than this value, the box will fall down. Okay, so, but we don't know what mu s is. It can have different numbers, right? You've seen the table for different material. There are different numbers. It could be 0.01, different numbers. It could be 1, even 2. It could be greater than 1. That's possible. If it's, let's say, if it's 2, if that friction coefficient is really, really large, then 9.8 divided by 2 gives you 4.9 meter per second squared. This is possible, not for humans probably, but in principle with a car, it's possible. For example, if you think about this Bugatti Chiron, it's one of the fastest cars in the world. It can go from 0 to 100 meters, 100 meters in 2.3 seconds. So let's calculate its acceleration. So it goes, so we are going to use this one. It starts from 0 velocity and it will accelerate. So I don't have v0t because initial velocity is 0. So it goes 100 meters in how many seconds? 2.3 seconds. So I take the square of it. And from here, if you do the calculation, the acceleration of Bugatti Chiron is 38 meter per second squared. So it's much larger than this number, right? So if you put the cereal box here and ignore the air resistance and the flow of air, everything, so the Bugatti Chiron can actually hold the cereal box here without, without having it slide down or fall down. If the mu s is smaller, then you need this much acceleration, about 10 meter per second squared. Still, Bugatti Chiron can do it. If you have the mu s as 0.1, then the acceleration that you need is 98, almost 100 meter per second squared. And for this case, even Bugatti Chiron cannot do it. What about a person? So the fastest runner one of the fastest runners in the world is Usain Bolt. So here you can see that there is a speed and time graph. This part is his acceleration initially. And after that point, of course, he cannot indefinitely accelerate. After some point, he will go with constant speed. But let's think about the initial acceleration part. So if you remember, the slope gives you in VT graph, the slope gives you the acceleration, right? Now, if you look at this slope, and so this point is about 10, this point is about 5.2. So subtract them, and then the time for that is about 1 second. So his acceleration is about 3 meters per second squared. Of course, this is initially, a person cannot accelerate indefinitely. Also the car, so it's usually the initial acceleration. So can Usain Bolt do it? Well, if he can do it, but probably it should have, there should be really, really large friction. So if μs is 2, he's not going to be able to do it because he can maximally do 3 meters per second squared, but what's needed is about 5. But maybe if μs is about 3, which is really, really large number, he can do it for this initial acceleration phase. So the movie, I think it was in Kill Bill, so it's not completely unrealistic. But of course, we are talking about only the acceleration part, the initial part. Because after your speed is constant, you can run really, really fast, but it doesn't matter. Even if you go with 1 million meters per second, if your velocity is constant, that means your acceleration is actually 0. So what keeps the box here, this is important, is not your velocity. Again, your velocity, if it's constant, even if it's 1 million meters per second, because your velocity is constant, your acceleration is 0. And if your acceleration is 0, you won't be able to keep it here. So what you need is acceleration. As long as you provide enough acceleration, you can keep the box here, not sliding down. Okay, let's move to the next section, which is about strings and springs. So let's say you have a rope like this. It could be a rope, it could be a string. When you pull on a string, let's say you're pulling from the both sides, some with force tension T, it becomes taut, it becomes tense. So the tension on the string is T at every point of the string or rope. So if the tension here is T, it's a force. At every point, it's T. So this tension here, it's pulling this part to the right, and this tension force. So if you are interested in this part of the object, you would show the force on it as T to the right. But if you are interested in this part of the object, it's pulled by this way from this part. Of course, at each point, every part of the rope is pulled in each direction, as shown here. So you can break here if you want and put 2 hands. It looks like this. So this part is pulled with T, and this part is pulled with T. So this section of the rope, there are 2 forces on it, and because they're equal, the rope really does not move, so it's stationary. But the important point here is, again, at every point on a string or a rope, it's the same, and the amount of force is always T. So the tension at every point, we said this, on a massless rope, string, wire, is the same. The wire is also just like a rope or string. So if you have an object set up like this, the tension here and on the rope, the tension here, it's always the same at all points. And we will also deal with pulleys. So the pulleys, in this chapter, we will deal with massless pulleys. We will assume they are massless. So massless pulleys don't affect the tension on the string. So the tension at every point is the same. So if you have a massless pulley, if the tension is here T, then the tension at every point, even after the pulley, will be the same T. So that means if this person is pulling the rope with force F, let's say 10 Newton, then 10 Newton tension, and the tension here will be 10 Newton. So that means the box, the crate, is pulled up by 10 Newtons. So the point here is massless pulleys, they don't affect the tension on the rope. But that conclusion is not valid for if the pulleys have mass in the other lectures. In the future, we will see that what happens if the pulley has a mass. But for now, just massless pulleys. Okay, so let's look at these three setups. So all of these blocks are stationary. So stationary means they are not moving at all. So for the first one, so for all of them, I will use this coordinate system. If they are stationary, that means they're not moving. The acceleration is 0. Okay, so for the first one, how would you write F equals ma? Well, there's no x motion, so you don't even have to write it. So there are really no forces on the x direction. In the y direction, if you have the scale, let's say you read the force is T, or the weight, that means this block is pulled up by T. So the net force in the y direction will be T minus mg. So the mass is 1, so mg becomes just 9.8 because m is 1 in this problem. So you write T minus 9.8, m is 1, but because the system is stationary, acceleration is 0, so this part is 0. Then T equals 9.8 newtons here. Again, why do we have not 9.8 minus T, but instead we have T minus 9.8? This is again related to the coordinate system that we chose. What about this situation? Let's say again you are reading on the scale T, maybe that's what we're going to find, in fact. So that means this rope is pulled by tension T, and we are dealing with massless pulleys, so that also means tension here is T, and as a consequence, that translates here as this box is pulled by tension T up, and there's also mg. Again, just write F equals ma. The net force is T minus 9.8. Because it's stationary, it's not moving, acceleration is 0. In this case, also tension is 9.8. So as you can see that they look different, but they actually give the same tension. Now, what about this one? What would you read on the scale? If you have this setup, you can see that it's 1 kilogram here, 1 kilogram here. Obviously, this will not accelerate, right? Because the forces are equal. So just like as I said before, you have to focus on one object at a time, either this block or this block. You cannot think of both of them together. So if you, for free body diagram, if you're, let's concentrate on the one on the right. So if you read T on the scale, then that means at every point on this rope, the tension is T, and the rope is pulling it up, pulling the block up. So in the up direction, I have T, down direction 9.8. Again, I'm writing the same equation. Turns out, even in this case, the tension is 9.8. So this may be a little bit confusing. You may think that some students think that the tension should be actually 2 times 9.8, but that's not correct. It's not 2 times 9.8, it's 9.8. You may think that it's, if you compare it with this one, here you may say, well, there's only 9.8 pulling it down, but here the same rope is pulled by 2 of them in the opposite direction. So shouldn't it be 2 times 9.8? The reason is, the answer is no, because even so, when you have equilibrium, if these objects is not moving, you can think of this, cut this rope here and put it on the wall. So this turns into this problem. We are not really changing anything. So you can have a mass here, making the equilibrium, enabling the equilibrium, or you can have a wall, and this is tied to the wall. It's the same thing. So that's the reason where in all of these cases, the tension is the same. Okay, here is one of the classic questions of pulleys. So it says find F to pull the crate up with constant speed. So constant speed, it basically means, zero acceleration. Okay, so zero acceleration, remember, it may mean zero speed or constant speed. So if the person is pulling it down from here, so that means the force here, the tension, it's F, because it's, the person is pulling it with F down. And the force, the tension here is F because this is the same rope. And all the way up to here, it's the same rope. So here F and here F. So if you think about this pulley, these two Fs are pulling it down. So if you're interested in this pulley, they're pulling it down like this, 2F. So in total, 2F, and that 2F would be pulling it up so that it becomes in equilibrium or zero acceleration. But we are not really interested in this part. We are actually interested in the crate. So these two Fs, if you are interested in this pulley, you have to think of them as pulling up. So force F and force F, those two forces are pulling it up. Okay, and so if 2F is pulling up, that you can have it here. That will mean 2F is pulling up the crate. So what are the forces on the crate? So we are interested in the crate. The other force is mg. So it's basically the weight, mg. Okay, so let's write down. So if you want, we can do also the free body diagram here. So we have 2F and we have mg. The question is, what is F so that this moves up, the crate moves up at constant speed, which means zero acceleration. So acceleration in the y direction would be 0. So let's write F net y equals ma. Okay, before writing these forces, I need to decide which direction is positive. Well, I can take up direction to be positive. So this is the coordinate. So then 2F comes with positive sign and mg comes with negative sign. Okay, and they're going to be equal to 0 because ay is 0. Okay, and from here, F equals, so put mg the other side and divided by 2. So this is the amount of F. M is 52. G is, let's say, 9.8 divided by 2. And the answer is 255 newtons. So if you pull this rope down with 255 newtons, this crate will go up with constant speed. It will not have an acceleration. But if you pull it, let's say 256, more than 255, then this crate will actually accelerate in the up direction. So this is basically the force that's needed for zero acceleration, which means constant speed. Okay, let's continue. Now we are moving to springs. So these things are springs. They can be extended or compressed. So the formula that we are going to use for spring force, it's given, it's Hooke's law. It's given as negative k times the compression or extension. So that x is either compression or extension from the equilibrium position. And k is the spring constant. It's some number, and it depends on the spring. So some springs, it's hard to compress or extend them. If it's a strong spring, that means k is large. But if it's a weak spring, then k is smaller. So if there is no force on the spring, no extension, zero force. So this is the equilibrium position. That's 0. Let's put it here. That's the equilibrium position. If you extend it for the distance of x with force F, what happens is then you can use this formula to find either force or x from whichever is given. So let's say, so you're holding the box like this, and the spring will pull it in. So in this case, this force, it will be negative k, so it's in the negative direction, times this extension amount. So if you pull it more, the force will be more. In fact, if you pull it for 2x distance, the force will be actually 2f, because you can see that x and f, they are linear. Or you can do compression, but the formula is still the same. It's f equals negative kx. So the thing is, why you need a negative sign here is because if you extend it, if you pull it to the left, the spring actually tries to restore its original position, so it pulls the box to the left. If you squeeze it, if you compress it to the left, then the spring pushes the box to the right. So that negative sign comes from there, where it basically tells us that Hooke's law is in the opposite direction to the position. Okay, here we move to section 6.3, translational equilibrium. Translation means having an object and moving it to another point, either in x direction or y direction, or negative x, negative y. Translational equilibrium means the object is not moving to the left, to the right, or up or down. So basically, the object is standing still at its original position. So when do we call it translational equilibrium? Well, all the forces in horizontal add up to 0, and all the forces in vertical add up to 0 as well. So the object is stationary. So if you have a flower like this is the physical picture. So what forces are there on here? You can think of this, maybe this point. You can think of this point. So there is the force mg coming from the flower, mg, and there is the force tension for this piece of rope. It's pulling it to the right, and there is another tension on this rope. If you draw the free body diagram, it looks like this. So there's mg, there's tension 1, and there's also tension 2. And this angle is given to be theta. Now, in this case, I would use this coordinate system. So I would like to have all the forces, all the diagonal forces like these. I would like to find the components so that everything is on x-axis and y-axis. So this component of T2 would be T2. So I'm going to use this angle. So I have to write sine theta. And for this component, it's going to be T2 cosine theta. Now I can redo my free body diagram. So in the up direction, it's sine theta. There's mg, there's T1, and there's T2 cosine theta. So what are the equations that I can write if there's translational equilibrium? In the problem, it usually says, you know, what should be the tension or the mass or the weight so that the object is in translational equilibrium. So in that case, what you do is this force, the up force, should be equal to down force. So I can write T2 sine theta equals mg. And the other equation is T1 should be equal to T2 times cosine theta. So these are the conditions for translational equilibrium. So these formulas, they are also coming from, you can find them from F equals ma as well, F net equals ma. So if you write F net in x direction equals max, well, because there's translational equilibrium, it's not, the object is not moving, no acceleration. So this will be 0. So for x, let's say, so I would write T1 with positive sign. And T2 cosine theta will come with negative sign equals 0. And from here, it will be T1 equals T2 cosine theta. And this is exactly the second condition. So either way, you can start from F equals ma, but we already know in translational equilibrium, AX is 0 and AY is 0. So you can do a shortcut here in this case. You can say all the forces up should be equal to all the forces down, and all the forces to the right should be equal to all the forces to the left. So that's the shortcut. But in principle, it's coming from actually F net equals ma. Okay, if the objects are stationary, which means they are just not moving, that's the case here. Let's write down the equations arising from translational equilibrium. So we have such a setup here. So there's this mass here B, there's the mass here A. You may think that the A would go to the right and as B goes down. Well, if there was no friction, that would be true. But in this case, there's a friction between block I, the block A, and the surface of the table. So that friction, in this case, is enough to keep the setup like this. So what are the equations that you can write? Let's start with object A. So what are the forces acting on object A? Well, there's the mg. So ma times g. When you have several objects, don't forget to write the indices of the masses, because you will write these in equations so that you don't confuse them. And because it's on the table, there should be some normal force. And there is this, so this rope, the tension is, let's call it T2. So for this object, A, the effect of T2 is pulling it to the right, like this. So in equilibrium, translational equilibrium, the equations that I can write is T2 equals F. T2 is equal to the friction force. And NA equals weight. So these are the equations that I can write. Now notice that I don't put vector signs on them. because if you put vector signs, you have to put a negative sign. What I mean here is I'm just interested in the magnitudes. So it says if T2 is 5 newtons, then friction force is also 5 newtons. If I write the vector signs, then I have to put negative signs here because they are in the opposite directions. But just work with the amplitudes, that's fine. What about object B? It's the easiest here. It has the mass times, it has the mbg, the weight, and there is this tension. So for this one, we call this T1, tension here, T1, and for this rope, the tension is T3. So this tension, the rope, it's actually pulling object B up. So there are just two forces. So T1, the magnitude of T1 is equal to the magnitude of the weight, which is mb times g. Now finally, let's think about this, this point. We can write an equation about it. So now, as we did in the previous slide, you have to, the problem here is this diagonal. Whenever you see a diagonal force, you have to find the components. So this component will be T3. So if this is 30 degrees, then I have to use sine here, sine 30. And this one is, because this is close to the angle, this is going to be cosine 30. Okay, what are the equations here I can write? Well, T2 should be equal to T times cosine 30, which is here. And T1 should be equal to T3 cosine 30, which is, sorry, sine 30, which is here. So in a typical problem, it could ask one of these things like you could ask T1, T2, T3, or maybe masses of these objects, so, or even the friction force. Or sometimes it may ask, what is mu, the friction coefficient here? Of course, it should be static because this object is not moving. In that case, you would find the normal force. And then, you know, F is defined to be mu s times normal force. So if you know the friction force, and if you know also the normal force, then you can find mu s from friction force divided by normal force. Normal force in this case is just mag, so it will be Fs divided by mag. Again, the same question. Normal force is not always mg, but sometimes it's mg, and in this problem, it should be mg. Because there's equilibrium, all the forces up equal to all the forces down. In fact, it's here, which gives us just mg. Okay, so what about these problems? How do you solve the problems involving an incline? Now, if you look at this setup here, you cannot really tell if this is going to go down with this small mass, if it's going to go down or up. So we don't really know, but let's do two possibilities. In this case, in the first possibility, the object m, small m, lowercase m, it goes down. So this m goes up the incline. So in this case, the acceleration is for this m, the acceleration is in this direction. Now, because these are connected with the same rope, this should have the acceleration in the down direction. Now, in problems like this, when you have a rope, and especially with the problems with the inclines, the coordinate system is following the string. So you choose a coordinate system which follows the string. So this is the string or the rope. So I will choose anything that's along this string and in this direction to be positive x. For example, for this m, I will choose this direction to be positive x and follow the string, and down direction becomes positive x. Why do I choose not the opposite? Because I am choosing the positive direction. in the same direction as the acceleration so that I don't have to deal with negative sign when I write acceleration. Okay, so what are the equations that you can write here? First, I don't know what the tension is on the rope, but I'm going to call it a variable, just T. If it's tension T here, it should be also T here. Okay, let's write down the equation for lowercase m. So what are the forces on it? Well, there is this tension force up, and there's this mg, lowercase mg. Now, what is the equation that I'm going to write? I'm going to write F equals ma in this direction. And so which one is going to come with positive and negative signs? Well, here the down direction is positive, so mg comes with positive sign. So mg, t comes with negative sign according to this coordinate system. And it's going to be equal to m. Now acceleration, I chose it to be down. So down is, according to this coordinate system, is positive. In fact, that's the reason that I chose this coordinate system, so that I don't have to write negative a here. So I'm writing a positive a. So that's this equation actually, same thing. Okay, now let's move to this larger mass. So let's write down the forces. First of all, it has uppercase M, G as its weight. Now there's definitely a normal force because it's on the surface. So that's normal force. And there's the tension, which is pulling it up. So that's the tension force. And there's also friction force, which is in the opposite direction. Why is it in this direction? Well, it should be also kinetic friction because the object is moving. Why is the friction down? Because this object, we already decided to consider the situation where the acceleration in this direction. So if m is accelerating up the slope, then the friction force should be in the opposite direction. Okay, so now if this is mg, now look at the coordinate system here. The coordinate system, you can think of it, we are using x and y like this. Let's think about y coordinate first. So the normal force will be equal to, so what is this component of the weight? So it's uppercase M, G. Now if this is theta, this is 90 minus theta, and this angle is also theta. Okay, so this is going to be mg cosine theta. Okay, so n equals mg cosine theta. You can write this. You can either do F net equals ma, acceleration in the y direction is 0, and you would write n minus mg cosine theta equals 0, which would give you this. Now, I did the shortcut that I just taught you in the previous slides. If there's equilibrium, no acceleration, you can say all the forces in opposite directions should be equal to each other. So now let's consider the motion in x direction. So now what are the forces in the positive x direction? Well, there is T. Okay, is there any other force? No, that's only the tension. In the opposite direction, there is the friction, kinetic friction force. And not only that, there's also the x component of mg, which will be mg. Now I'm using this angle here. So this component is far away from it. So I have to use the sine theta. So mg sine theta. And it's here. So there are three forces in the x direction. Now, I have to equate this to ma. Now, one of the common mistakes here is writing wrong m. You have to be careful. Which object are we dealing with? The large m, the uppercase m object, right? So I have to use its mass, not lowercase, but it should be uppercase. This is one of the common mistakes that students do when they solve problems. Okay, and that was the third equation that I can write. So you have three equations you can solve if solve for any variable here. Okay, what about the situation where the system is the acceleration in the opposite direction? So the large mass is going down the slope and the small mass is going up. Now, what would happen in this case? Well, let's again start with the small one. So the tension is T. So I'm calling the tension on this rope. It's the same rope, so it should have the same tension. So there's going to be T up and mg down for the small one. Now I'm going to write F net equals ma. F net in the x direction equals ma. Here the x direction for this one is up, and for the large mass, it's down the slope. Remember, now our coordinate system is such that it's following the rope. So from this, what you find is now t comes with positive sign. Look, here t came with negative sign because of this coordinate system. Now the coordinate system is up here, positive is up. So now this time, t comes with positive sign, and mg is coming with negative sign. So this is the first equation that you can write. Now the other equation you can write for m, well, pretty much everything is the same except the friction force. Now, mg is the same, and we have n. So this has component again, well, this should be uppercase m, uppercase mg cosine theta. These are actually the same, right? No difference. Uppercase m, g, sine theta. Okay, now the only difference is, let's also write T, tension. So even though this object is going down, if the connected rope, the rope is actually not pushing it down. The rope is always pulls it. So the rope is pulling it to the up direction. Okay, the same here. Now the only difference is the direction of the friction. Now because this object is now going down, remember, friction force is always in the opposite direction to the motion. So now this friction should be in this way. Okay, so for x, so this will come with positive sign. Now look at the direction of positive x. So down is positive, so it comes with positive sign here. And there's a negative t, which is tension in the opposite direction, and Fk, kinetic friction force, is also in the opposite direction. Again, don't forget to use the capital M, uppercase M, for this equation, because we are writing equation for this one. And finally, you can also write the equation for normal force. Normal force should be equal to this force, which is here. So you may be wondering, which direction should I take? Like, how do I know when I see a problem like this? How do I know if this is going to accelerate down or up? So usually you don't know the direction of the acceleration a priori. So initially, by just looking at the problem, you can't tell it. In that case, choose any direction as the direction of acceleration. Then calculate the acceleration. So you choose any direction. Let's say you can say, okay, I'm going to assume that this is going in this direction. And so do your calculations, okay, find the acceleration. If you find a positive number for the acceleration, you guess the right direction. So you chose this one, and the acceleration turns out to be, let's say, positive 5 meters per second squared. That means, if this positive sign means you initially guessed the acceleration in the right direction. in the correct direction. So if you find negative number, that means the value is correct, but the true direction of the acceleration is in the opposite direction to that you guessed. So let's say you chose this direction and then you calculated -5 meter per second squared. And in that case, you should understand from this negative sign that the acceleration, even though you chose this direction and made the calculations according to this this direction of acceleration, it's actually the correct direction of the acceleration is down. So that means this negative sign means this is actually going down. Okay, so let's continue with connected objects. So when you have blocks like these, say connected objects, there's M1 and 2, and they are connected with a thread. So, or a rope or a wire. So if you pull these objects, what happens? If you pull it to the right, then there will be also usually friction on here and here. Those frictions are, the values are different usually. So let's write down the equations. So for this one, the first equation is, well, you can do the free body diagram if you want. So the force is in this direction, and the tension on this rope is T. On the first object, that the effect of that tension is pulling it to the left. So it's going to be T. And the friction is in the left direction. So let's put it here as well. That's the friction. So if you choose this coordinate system, F comes with positive sign, and these two other forces comes with negative signs. And then you should equate it. So we are just doing F net equals MA. So you should use the correct mass. Just don't write M. In this case, there's actually no M. There's M1 and M2. So for this block, it should be M1 times A. What about the second one? For the second one, there's actually no external force, but it's only T to the left and friction force to the left. Sorry, T to the right and friction force to the left. Now look at tension. On this block, the effect of tension is pulling it to the left. On this block, the effect of tension on the rope is pulling it to the right. So this rope is pulling M1 to the left, but it's pulling M2 to the right. Okay, so for this one, it's going to be, well, it's very similar to this one, but we don't have external force, and T comes with positive sign to the right. Friction again comes with negative sign, and here you have to use M2. Now, if you notice that I'm using the same A, I'm not writing A1 and A2. Why? The reason is these are connected objects. When the objects are connected, then the acceleration should be the same. In fact, we can go back to the previous slide. If you remember, for this large object and this small object, when we wrote F equals ma, we actually use the same acceleration. Why? Because they are connected with a rope. If this one is accelerating more than the other one, then this rope would break. So if the force is too large, the external force F, then M1 will accelerate quickly and the string between the blocks will break. In fact, this is something that you see every day. If you pull the toilet paper slowly, it comes down, but if you jerk it, jerking means pulling it really, really fast, then it breaks. How can we understand this? Well, if you think about this portion of the toilet paper, okay, so what are the forces? Well, one of the forces is the force that coming from the hand, it's pulling it down. The other force is coming from this part of the toilet paper. You can think of this as maybe some string or rope. It's actually pulling it up. So if you pull it slowly, that's the equation. F, let's choose acceleration down, positive direction to be down. So F minus T will be the acceleration. So if the force is huge, then the force here, the tension becomes huge as well. And in that case, this part of the paper cannot really hold it, so it breaks. Let's continue with Atwood machine. So in this case, we have two masses, but they're different. So M1 is smaller, M2 is larger. They're supported by the same rope, so they should have the same tension. If you look at the picture, you can easily say this is going to go down. So this large one is going to go down. The small one will go up. So there's no ambiguity. It's easy to tell. If you write down, so if you find the acceleration direction, so we know that this is going to accelerate clockwise if you want, which means this will go down and the other one is going to go up. So once you find the acceleration direction, now you can put your coordinate system in a way that it points in the same direction as the acceleration, the positive x-axis. In fact, in this one, we don't need y, it's just x. And you can see that here it's in the up direction. So the coordinate system is actually following the rope. So for this object, its up direction is positive. For this object, down direction is positive. You can do this when the objects are connected with a rope. So let's draw the free body diagrams. For this one, for the small object, tension is up, M1G is down. For the large object, it's the same thing. T is up, M2G is down. Now, the only thing that you have to be careful here is when you write F net equals MA, the direction for the coordinate systems for each one is different. Again, just think about X. So for this one, when you want to write F equals MA, so we are writing F net equals M times M1 times A. And for this one, F net equals M2 times, again, the same A. Why is the acceleration the same in both equations? Because these two objects are connected. So they should accelerate at the same rate. So for this one, the tension, it comes with positive sign. Why? Because up direction is positive, see? Comes with positive. But in this case, the tension is coming with negative sign, because for this part, for the large object, down direction is negative. Sorry, down direction is positive, up direction is negative. That's why we have the negative sign here. Here, M1G comes with negative sign because down is negative. Here, down is positive, so that's why M2G is coming with positive sign. And on the right-hand side, we always have the positive numbers, positive acceleration. The reason is that the acceleration for the small one, remember, it's in the up direction, which is positive for this coordinate system. And for this one, for the large object, it's going down, the acceleration is down, and it's again positive with respect to this coordinate system. Again, first determine the direction of motion. So that's the direction of acceleration. In this case, we can, by just looking at the figure, you can easily say the large one is going to go down. And then choose the positive direction in the direction of acceleration. So in this case here, we have two options. You can either choose this direction to be positive, or you can choose this direction to be negative. But again, if you choose the direction of acceleration to be positive, you wouldn't need any negative signs here. So that's the ideal case. That's the ideal way, that's the straightforward way to solve it. And once you have two equations, for example, you can calculate tension here, or other things. You know, if you know m1 and m2, if the unknowns are tension and acceleration, you can solve for both of them. Why? Because you have two equations and two unknowns, which is solvable. Okay, now we are moving into circular motion. It's we will use F equals ma again in this section. So an object moving in a circle must have a force acting on it, otherwise it would move in a straight line. So I have a recording here, which I did by using my son's toy train. If I turn it on, it just goes straight. So that's what it says here. If there's no force acting on the object, then it would just go straight. If there's a force, now you will see. So probably you see that there's a string there, which I connected to the head of the train. So if I pull the train to the center, now it makes a circular motion. Or we can say it this way: for a circular motion, there should be a force that pulls it at every time towards the center. So here it says the direction of the force is towards the center of the circle. Since acceleration and force are in the same direction, acceleration is also towards the center. And you will see that in the next slide, the direction of the force and the acceleration. But the point here is, if I pull it all the time towards the center, then it makes a circular motion. Or in other words, if there's a circular motion, that means there's some force that pulls it towards the center all the time. And you see what happens if I stop pulling it towards the center, then the train goes straight. So an object moving in a circle must have a force acting on it, otherwise it will move in a straight line, on a straight line. So that's, we already saw. So the direction of the force is towards the center of the circle. Okay, if there's a circular motion, if this is some object going in circles, it could be actually Earth around the sun, it could be moon around the Earth, or it could be a car going in a circle like this, or any other object, a toy, train connected to a string. So the direction of the force is towards the center of the circle, the net force. The direction of the net force is towards the center. There may be other forces, maybe in other directions, but if you find the total force or net force, it should point in towards the center. The center is here. The acceleration and force are in the same direction. We know this from Newton's second law. So acceleration is also towards the center. So this is the velocity of the object at different points. It's tangent, right? It goes around. And the force, you can see that the net force, it changes all the time. The direction changes. And it's always pointing towards the center. Same for the acceleration. We will call this force a centripetal force. Centripetal means center seeking. So it's always that force is pointing to the center. That's why we call it centripetal force. And the acceleration, we call it centripetal acceleration. So we will use this CP subscript to mean centripetal. Some algebra gives us that centripetal force, acceleration, sorry, the definition of it is this velocity squared or speed squared divided by the radius of that circle. So details of derivation of this definition here, the centripetal acceleration, you can find it in the book if you're interested, but in this class we will not derive it. But if you're interested, as I said, you can check out the textbook. So now let's apply Newton's second law. So we have this object here. It could be anything: toy train, Earth, moon. Let's call its mass m. So Newton's second law of motion, it's the same, except now we have these centripetal center-seeking subscripts. Now the other difference is now this centripetal acceleration has a definition. We can write it in terms of v squared, this velocity, divided by r. So if you apply the Newton's law, Newton's second law, F equals ma, then you end up with this equation in circular motion. Now you should be careful. Here we see FCP, centripetal force, is not a new force. It's the net force in the radial direction. Radial direction means towards the center. You know, x direction is this way, y direction is up or down, up and down, and the radial direction, if this is the center, is towards the center or from the center. So radial direction is getting close or getting away from the center. That's what it means. Now, this FCP is not a new force. So there may be, in this case, let's say there's some F, maybe there's some force, let's call it F2. In that case, the net force, the FCP, so in this case, FCP would be, so towards the center, we will take positive direction. So this comes with positive sign, minus F2. F2 is away from the center, so it comes with negative sign. So, and you would equate it to mv squared divided by r. So the point here is that I'm making, FCP is not a force that you would show on the free body diagram. Remember, when we write F net equals ma, on the free body diagram, we show all the forces, not F net. F net is the net force, the resultant, the total force. It's not something that we show on the free body diagram. So again, here FCP is the centripetal force. It's the net force in the radial direction. So maybe write it here. FCP is the net force in the radial, which means towards the center of this circle, in the radial direction. So maybe you learned, some tricks in high school to solve such questions quickly. Maybe you showed forces in the opposite direction, like outside, from the center towards the other positions. Now you have to forget about those methods. They are not correct. Yes, they get you the solution quickly, but they will not work in all the problems that you will see in this class. So you should really, forget about those fictitious forces that you may have used in high school, but learn this method. So this method tells you that if there is a circular motion, there is definitely a net force towards the center. For example, if F2 is equal to F, you cannot really get circular motion. Why? Because F net in the radial direction, this would be, FCP would be 0, right? If F equals F2, this would be 0. So you would not get any circular motion in this case. Okay, this force, FCP, may be provided by the tension in a string. That's a possibility, which you can see here. Or it could be normal force, it could be friction, it could be a gravitational force. This is the case with the Earth and the Sun, or Moon and the Earth system, or others. So the bottom line is there is some force that pulls the object towards the center. And in that case, you would get circular motion. So which coordinate system should I choose in circular motion? We don't choose x and y as like static coordinates. We choose the coordinate system. It's wise to choose the coordinate system where the positive direction is pointing towards the center of the circle, so that ACP always comes with a positive sign. So for this circular motion, we will choose towards the center. So here in this case, this way, to be positive. You can call it positive x if you want. So any force that points towards the center, we will take them with positive sign. And any force, if there is any force that's away from the center, we will take them with the negative sign. Here, for this one, this person is swinging this ball, which is connected to this string. So if you want to write the free body diagram, you can show it like this. So there is only one force, which is T. Of course, there's mg, but we are not interested in that force in this case. So it's pulled in. We are interested in circular motion here only. So I didn't put mg, but of course there is mg. So how do you write F equals ma for circular motion? Now, remember, for circular motion, we are going to use F equals ma, but with Cp subscripts. And we also know the definition. This is V squared divided by R. Now, what are the forces here? Well, it's only T, and it's towards the center. This is center. Now, if it's towards the center, I will take it as positive. Here, it's positive, and equals, it's m times acceleration, centripetal acceleration, which is V squared divided by R. Now, look at this formula. We can interpret it. What happens to the tension, let's say, if we increase the velocity of the object, well, the tension increases. If it's a massive object, this ball, if you make it more massive, then the tension increases. If you increase R, which is the length of the string in this example, then the tension decreases. So you can interpret this equation in that way. Here's a warning, which I talked about a little bit before. FCP is not a new force. It's the net force in the radially inward direction, so towards the center. Radially outward direction is, so radially inward is positive. And if you have any force radially outward, which is F2 here, you can see that it's radially outward, then it will come into the equations with a negative sign. So FCP is like Fnet in Fnet equals ma in the linear case. Remember, we never showed Fnet on a free body diagram. Fnet was the net force of the combination of actual forces. Those forces could be tension, normal force, friction, weight, etc. Similarly, FCP, centripetal force, is the net force towards the center when there is circular motion. Let me show you that through this example. So if you have this object, let's say there are two forces. One of them is F1 towards the center. Maybe there's a string here. And there's also another force. Maybe it could be a wind, wind coming from the center. Maybe a fluid flow, maybe some flow. It could be liquid or it could be air, which is radially outward. And let's call that force F2. Now, this is a circular motion, so I'm going to use FCP equals MACP. The thing that you have to be careful here, again, is the signs of the forces. So F1 is radially inward direction, so it will come with a positive sign. F2 is from center, it's to the outside, so it's radially outward, so it will come with negative sign. And m is the m here, and ACP is, remember, we know the definition, v squared divided by r. So for this system, this is the equation. Okay, so of course, this radial motion and these equations, they have applications in the daily life. For example, the cars. What makes a car go in a circular motion? Here, it's going in a circular motion, or turn a bending road, or it could be, turning this road. So what makes a car go? So what makes the car here not go away from the, fly away from the road, but it's kept on the road? What is that force? That force is actually static frictional force between the road and the tires of the car. The car would normally go straight, remember, from the Newton's laws. If there's no force, then, or just like the toy train, they would go straight if there's no force that's pulling them to the left or right. But this Fs, static friction force, which is shown here, so the car would go like this, straight, right? Well, that is not very straight, but so kind of like this direction. But this friction force is actually, which is between the tires and the road, it's actually pulling the car towards the center. Center is somewhere here all the time, just like I pull the toy train to the center. So this friction force, static friction force, is pulling the car towards the center all the time. Now, maybe you got the question that I said static friction force, but the car is moving, right? So I said this friction force is static force. Why? Even though the car is moving, how is it possible? Why don't we use kinetic friction force? Now, the reason is because the car is static, which means not moving, in the radial direction. That is, the car's radius is always r. Yes, the car is, this is the circle. Let's say the car is moving in circle, on the circle. Okay. Yes, the car is moving on the circle, but the car is not moving radially. The radius of the car is not changing. So the car moves forward, but the car is not moving sideways. So that's why, in sideways motion, we will think about it as static. In the r coordinate, in the radius, the car is static. That's why we are using static frictional force. Okay, so let's look at the forces on the object. Now, because we have friction force involved here, and you know that to be able to find the friction force, we need mu static times n. And the normal forces now here is related to y axis, so we have to also include the y axis. So first I'm going to write F equals ma for circular motion. What are the forces radially inward or outward? Well, there's only actually one force in the radial direction. It's just the friction, static friction. And m is here, and this part is just centripetal acceleration. That's the definition of it. Now, friction force is mu s times normal force. Okay, and this right-hand side is the same. Now, what is normal force in this problem? If you look at it, there's no acceleration up or down, so you can use the shortcut. You can write F equals ma for y, but you can use the shortcut because there's no acceleration. You can say just n equals the weight. Weight is mg. I mean, there's no other force in the y direction, right? There's one up, which is normal force, and one down, which is mg, so they should be equal. So then normal force is mg in this problem, but in this problem it's mg, but keep in mind, in other problems, normal force may not be equal to mg. In fact, you have seen examples, sometimes normal force is mg times cosine theta, or it could be some other thing depending on if there's external forces, whatnot. But in this problem, mg. Okay, so now I can cancel these m's. So the final result is mu s times g is equal to v squared divided by r. So let's say you're going to design a road, okay, and you want people to be able to take this turn on this bending road with some velocity, maybe 100 kilometers per hour, maybe. And maybe the radius is, let's say, 50 meters. So think about a circle with radius 50 meters. G is known, it's 9.8. So if these are the conditions, so you want people to be able to drive 100 kilometers per hour for this radius, then you can find from here what should be the static coefficient, friction coefficient between the road and the tires. Or you can go the other way. Let's say you know the static friction force. Usually you cannot really change it because it depends on the tires and the road. It's usually, there's not much freedom to change it. G, you cannot really change it. It's fixed. So you know this one, you know this one. And if you know the radius as well, you can find the velocity, the safe velocity, or the maximum velocity that is safe for this car to be, so that it makes a circular motion, so that it doesn't go outside the road, it doesn't slide out, or it doesn't spin out of the road. So depending on what's asked in the problem, you can solve either one, solve for either variable. But that's the equation. So this is the equation that connects the velocity of the car, the radius of the road, so radius of the circle, that's the road, and G and mu s. Okay, now here is a similar situation, except here we don't have, so we have a tilted road. So the road has some angle. In fact, most of the roads, the interstate or highway roads, they have usually this angle. In this example, we will ignore friction, but it can be added. So if there is friction, you would add it in this direction. Sorry. It will be added in this direction. It should be parallel to the path, the road. But you will see that in this setup, you actually, even without the friction, you can stay on the road without slipping. So let's consider that case. So let's say friction is ignored. Now let's calculate. Let's think about the forces on the object, on the car. Well, there are actually two forces: the normal force from the road, and the weight, which is mg. Okay, how do you find? I have to find this angle. So this is the free body diagram. Okay, is this angle theta, or is this one would be theta? How do you find it? Again, just make a triangle. So I'm going to use this triangle. Or you can use, another triangle as well. So if this is theta, let's make it connected. This is 90 degrees. If this is theta, this is usually given. Then there's a 90 degrees triangle. Look at the large triangle. If this would be 90 minus theta, because the total should be 180, right? So 90 here, add this one. So 90 plus 90 minus theta plus theta, it gives you 180. So that's right. If this angle is 90 minus theta, now look at this triangle here. So this is 90. This is 90 minus theta. Then this angle becomes theta. And now look at here, these two lines. If this angle is theta, then this one is also theta. So I need this theta because I have to find the components, right? So N has this component, the normal force has up component, and this component in the x direction. Now, also look at the coordinate system that I choose. Remember, the coordinate system in circular motion, the positive direction should point to the center. You don't choose this one. The reason is, this point is not the center. This car is going in circles. If so, the center of the circle, the center of this, think about it as a circular road. The center is maybe somewhere here, or you can put it maybe somewhere here. The center is definitely not here. So that's why this coordinate system should point in this towards the center. So I'm not taking this one, I'm taking this coordinate system. So positive x points to the center. That's why I'm finding these components. So if this theta, this part, then this closed component will be n times cosine theta. And the component that's far away from this theta will be n times sine theta. Now, the motion in y direction is up direction. So it should be n cosine theta. Now, I'm not really writing f equals ma, but because there's no acceleration in the y direction, I can use the shortcut. So all the forces in the up direction will be equal to all the forces in the down direction. So n cosine theta will be equal to mg. And from here, you can solve for, if you divide both sides with cosine theta, you can find n, the normal force is mg divided by cosine theta. Okay, now the motion that's radially inward, we are going to write f equals ma for that, but because it's circular motion, I'm writing them with Cp indices. Okay, so what are the forces in the radial direction? Well, there's only one force, which is this, right? There's no other force. In this problem, we ignored friction. If there was friction, we could also include friction. But in this problem, there's no friction. So the force, the net force in the radial inward direction is n times sine theta. Mass is mass. And for centripetal acceleration, it's v squared divided by r. Now, if you solve for, let's do, what we can do here is, we can plug normal force here. Okay, so it's going to be mg cosine theta here, mg cosine theta. What's left is sine theta. Sine theta is here. And on the other side, we have mv squared divided by r. So now let's cancel m's. Let's cancel m's. Here we get g times tangent theta. And on the other side, we have v squared divided by r. So again, you can see that for a given angle, there is an equation that relates the angle g, v squared, and r. So in this problem, you can say, for example, you can answer the question for let's say 100 kilometers per hour for radius of 50 meters. What should be the angle so that the car can safely be on the road, not sliding out, not slipping? So it could be on the road, or you can ask the other way around. Let's say, so that you know this is important. This equation is used to design these roads, design the tilt or the angle. But you can also ask the other way around. So if you're given, let's say someone did this build already this road, g is given, theta is given, so it's this road, say 20 degrees. Radius is given, then the question could be, what is the maximum safe velocity so that the car would be on the road without sliding out? Okay, Here's another example. Now, in this case, the car is not going to the left or to the right. It's actually going down, so going into a dip. But here you can see that, you know, this part is straight, this part is straight, but this part of the road is, it's actually circular like this, right? And you can think of this circle here. So the normal force from the road, of course, there is the normal force up because it's on the ground. There's the weight here. In fact, these are the only forces. So the normal force from the road on the car is more than its weight when the car goes in a dip. Let's prove that by using the F equals ma for the centripetal motion. Now, the center of the circle here, it's now somewhere here. So I should take the normal force in the positive sign and mg with the negative sign. Remember, any force that points towards the center comes with positive sign, and the other ones comes with negative sign if it's pointing from the center in the outward direction. Okay, so normal force comes with positive sign, weight comes with negative sign, and the other part is just ma. So weight is mg. Now we got this equation. And if you solve for normal force, now just put mg on the other side with the positive sign. So the normal force becomes this one. And in fact, we showed here what is expressed in the statement. The normal force from the road on the car is more than its weight when the car goes into a dip. It's really the case. If the car goes into a dip, so the car is going in, it's making a circular motion. In that case, the normal force is more than mg. It's mg plus this extra term that comes from the circular motion. So it's effective. So the effect of circular motion is this part. Okay. Now, this one is interesting and tricky. So here's a question. A rider in a barrel of fun, and this is called barrel of fun, there's a woman inside and it turns with some speed. Okay, this barrel is turning, rotating with some speed. So that rider finds herself stuck with her back on the wall. So this person she's stuck on the wall. She doesn't slide down, she doesn't fall down as this thing turns, rotates with certain speed. The question is which diagram or which free body diagram correctly shows the forces acting on her? Are these the forces or are these the forces? So which one among these 5 cases show, there's only one which shows the correct direction of the forces. Now you have to find that one. Which one is it? You can pause the video here if you want. You can think about it. Now, the answer is the first one, A. The reason is, first of all, let's think about the forces. If there's a wall here, now whenever there's a surface, that surface would push the person. It will be a normal force, right? Could it be like E? No. I mean, the person really cannot push the wall, right? We are talking about the forces. Well, the person can push the wall. I take it back. What I meant to say is, there is no force on the person that pulls it towards the wall. I mean, there should be someone inside, maybe, pushing her in this direction, so that will be the case. But really, there's nothing that pushes her towards the wall. The wall itself pushes her towards the center, right? And that's the normal force. What about the other forces? Well, I think all of them, they have mg. There's no debate about it. So mg is given. But now, if the person is staying on the wall, if she's stuck on the wall, then there should be some force. So normally because of the mg, she would fall down, right? So there should be some force that keeps her on the wall so that she's not falling down or sliding down. So there should be some upward force like this. And that force would be the friction force on the wall. And it will be indeed static friction because she's not, she will be static in the up and down direction. So she's stuck on the wall. She's not sliding down, but there's mg down. So there should be a force in the opposite direction, which is the friction force. So the correct one is, the correct direction of the forces is shown in A. So the normal force N of the wall on the rider, okay, so the object that we are interested in, the person, not the wall, the person. Of course, the person applies some force in the opposite direction. It will be negative N, okay? But on the person, the only force that acts in the radial direction is coming from the wall. Is there any force on the person in this direction? No. So that's why so this cannot be. So don't think this is on the wall. This is actually still on the person. So to be able to have such a force, there should be, as I said, there should be someone that pushed the woman radially outward direction. But there's no such person or inside, any object that would do that in this case. So the normal force N of the wall on the rider is the net centripetal force here that keeps her going around the circle. The downward force of weight, W, is balanced by the upward static frictional force on her, so she doesn't slip vertically, so she doesn't fall down, and the reason for that is Fs. But again, Fs depends on the normal force, right? So you need some normal force so that there can be any friction. If there's no normal force, that means there's no friction. So there's no force pushing her to the wall of the barrel. So E is wrong, so this is wrong. So what happens is she wants to go straight on a straight line, not to turn, due to her inertia. Remember Newton's first law, objects are unwilling to change the magnitude or direction of their velocity. So this woman, she has some velocity, she would normally go this direction, right? So she would go straight on this direction. But what happens? So while she tries to go straight, the barrel turns and cuts her way. So she ends up pushing the barrel wall. So the barrel comes here, so she cannot really go straight, right? It's just like as I was pulling the train all the time. The train wanted to go straight. Train wanted to go straight, but at each moment, I was pulling it in. So at the end of the day, the train was actually making a circular motion. Same thing happens here. So she ends up pushing the barrel wall because the barrel cuts her in. So the barrel comes here, so she cannot go straight. So she ends up pushing the barrel. But again, this force is shown on the person. There's no force in this direction on the person, but of course on the wall there's such a force. Okay, so, and because now she pushes the barrel wall pushes her back. So this is the origin of the normal force N on the woman applied by the barrel wall. The reason she doesn't go straight or fly out is because at each moment, the normal force due to the barrel pushes her in. So that's an interesting way of thinking about circular motion, but you have to get used to this. If something is going in circles, like this woman here, there should be a force. It could be normal force, it could be tension, some rope, It could be gravitational pull between the Earth and the Sun. But the point is there should be a force towards the center. Again, remember the toy train, it wanted to go straight on a straight line, but I kept pulling it in. And what about falling down? Well, the reason that she doesn't fall down is the friction force. Also remember, for friction force, you need a normal force. If there's no normal force, then there's no friction force. Here we take static friction coefficient, mu s, because the woman is static, she's not moving, on the y-axis. So this is the y-axis. She is static on the y-axis. Now, if you write F equals ma for centripetal, for circular motion, then the only force is normal force, and on the right-hand side, I have m, and I have the centripetal acceleration. What happens if the barrel speed decreases? Well, if this part decreases, by keeping everything else the same, well, mass is the same, radius is the same. So if the velocity decreases, hence, normal force will decrease. If normal force decreases, the friction force will become less than mg, because normal force going down, friction force is going down. Now, if this force is less than mg, the friction force will not be able to support mg. And then in that case, when this happens, the woman will start sliding down, and in fact, she will fall down. So that's the end of this lecture. So see you in the next video.